um, the last lab exam. So I'd be happy to answer lab questions if you have anything. Some stuff with like position versus time graphs. Some stuff with figuring out what you know about the direction of the acceleration and net force. And some stuff. What else is left? Some free body diagrams. I think that's about it. Yeah. Yeah. Sure. Yes. Yes. Okay, so the first one, so let's say you have no, I'm trying to draw this all perspective-y like. He's really skinny because he's been training for the Tour de France. Okay, so let's say, what was the point of drawing this, I wonder? Okay, so let's say this guy's going like around this turn. It's a turn. That's supposed to be the idea. So let's say he keeps a constant speed as he goes around the turn. What do we know about the direction of the net force in a top-down view? Okay, so from above, I don't know if this is clear from my drawing, but it's supposed to be like going around a turn like this if you're looking from above. And constant speed. So how are we going to figure out the net force direction? Basically, the process is always, yes. It is in this case, yes, that's right. But I'm just going to go through the set of steps that just always works, and that's what I would recommend doing, just go through the steps. So first of all, the velocity is tangent to the path. There's no change in speed. It says that the speed is constant, and so there's no parallel part of the acceleration. There is a perpendicular part this way. Since the total acceleration is the sum of the parallel and perpendicular parts, this is also the direction for the total acceleration. And then Newton's second law says F net has to be in the same direction as the total acceleration, so F net is also in that direction. Yes? That's what, yeah, this picture with the vectors on it is supposed to be a bird's eye view. That's perpendicular. That's the part that's perpendicular to the velocity. Okay, so now so this is the first one. And then the second one, let's do a problem where we have a box that is slowing down as it, so that's the direction of motion, and it slows down as it slides up the ramp. And so I'm going to do two things with this. I'm going to go through an analysis to figure out what we know about the direction of the net force. And then separately, a different approach is I'm going to draw a free body diagram where, and so you can see like the difference in those two ways of doing it. Both are ways that you could use to calculate the net force, but they're totally different approaches. Okay. So first, it's the direction of F net. And then second, I'll draw a free body diagram. Okay, so for the first part, there's the object. Here's the path. Its velocity is this way because that's the direction of motion. It's slowing down. So the parallel part of the acceleration is opposite the velocity. It's moving in a straight line, so it's not turning. So there's no perpendicular part. And so that means that the total acceleration is the same as a parallel. It is a parallel. And now that we know that the total acceleration is down the ramp, we know that's also the direction of the net force. Any questions about that? Yes. Well, it depends which way it's curved, but if it was like a bowl shape, then the perpendicular would be that way.
Okay. This is directly opposite of, directly perpendicular.
Yeah. Yep. That's what the perpendicular means, is that it's perpendicular to the velocity. And then you have a perpendicular that way and an a parallel that way. So the total acceleration could be anywhere in that range of 90 degrees. And that means that F net could also be anywhere within that range because F net and A have to be in the same direction. Okay, so now I'm going to draw a free body diagram of this. Yeah, I'll just call it MG, but yes, to do a calculation, you would have to. Okay, so the free body diagram. We have the weight, and that's mg. And then now we're going around the boundary looking for contact. There's a pushing force from the incline, that's the normal force. And now presumably there would also be friction. So which way would the friction force act? Opposite the velocity, opposite the direction of motion. So it would be this way. And the magnitude of that would be whatever the coefficient of friction is times the normal force. Okay, so the free body diagram doesn't have F net on it anywhere. It only has the individual forces. And if you added up these three individual forces, the sum of those would be the net force. And so from thinking about this two different ways, well, I lost my arrow here. From thinking about this these two different ways, we know that if we added up these three vectors, we get a vector that was in that direction, which actually you could use to calculate some ratios and stuff, but it doesn't end up being a very useful way to do it, I don't think. Any other questions about those? If you add up all the individual forces, you get F net. That's just what F net is. And then from that, you can calculate the acceleration from Newton's second law. Any other questions? Yeah. I just assumed that if that box is sliding up there and I didn't say anything about it, there was probably friction, but just to make my picture look more interesting. Because I mean, in a real problem, I would hopefully make that clear whether it's there or not. Calculations. Yeah, a problem like this. I mean, I would give you I would tell you what the coefficient is and what the mass is, and then you could calculate that acceleration. Not on the lab exam. Oh, okay, right. Only in the in-class, the regular exams, I do that kind of stuff. So the closest you'll get to those kind of problems is just drawing the free body diagram. Okay, so how many forces are acting on that block? 3, yep. What about F net? That's acting, right? Well, F net is just, you take all the individual forces and add them up, and that's F net. So this has 3 forces acting on it, and if you add those 3 up, it gives you F net. That's sort of the relationship between those. Any other questions? I don't have it yet. I don't have it graded yet. Maybe Thursday, hopefully Thursday. Yep. There's a quiz on Thursday. Yes. Yes, I think that's a good idea. Okay, just made that decision. I probably would have put it on anyways. Any other questions? Okay. So now we're going on to a new topic, sort of new. We're still using Newton's second law, but now we're going to do calculations that only involve circular motion. And really most of the sort of directional thinking and stuff that you need for circular motion is stuff that we've already done in lab. So if you have an object that's moving along a circular path, let's say it's here, and let's say it's slowing down. What do we know about this motion? Well, the velocity vector is this way. If it's slowing down, then the parallel part of the acceleration is opposite the velocity. It's turning this way, so the perpendicular acceleration is this way, and it's always right toward the center. And then since we're going to be doing calculations, we're not going to have to think about the direction being in a 90-degree range or anything. We're just going to do the calculations. Do the calculation. The total acceleration is equal to a parallel plus a perpendicular. And none of that is new. Right? This is the same thought process we've been following in lab for a while. There really are, I'm going to call, I think it's just 3 new things. Okay. So there are only 3 new things. The first one, okay, 3 things isn't very much, right? There's not very much new. The first 2 things are just new names. It's not even new concepts. So this is going great so far. So for circular motion, what we used to call a parallel, what we call a parallel general things, is now called the tangential acceleration. And I'll denote it A tan. And notice that's a very reasonable, that would have been a reasonable name even for motion that isn't circular. To find a parallel, it's always tangent to the path the object's moving along, no matter what the shape of the path is. And so tangential acceleration, that's a great name, better name than a parallel. The second thing is for circular motion. A perpendicular is now called the centripetal acceleration. Okay, that's a stupider name. I'm going to denote that ACen. Okay, why'd they give it that ridiculous name? Well, centripetal means toward the center. And when you're dealing with circular motion, this is actually a place where circular motion is quite a bit simpler than, it doesn't take as much thinking as general motion like we do in labs. The perpendicular part of the acceleration is always toward the center of the circle, right? So dot in the center, the centripetal acceleration always points right to the center. So that's why it has that name. And then the third one, this is the only one that's has some substance to it, really. Magnitude of the centripetal acceleration. This one's kind of amazing. if you're easily impressed, like I am. The magnitude of the centripetal acceleration is v squared over r, where v is the object's speed and r is the radius of the circle. Well, let's make sense out of that, first of all. So, do you believe it? So, think about driving your car around in circles in a parking lot, like a big parking lot, okay? And we'll start out at like not going too fast, like 10 miles an hour, going in a fairly big circle, you know? Your body is a good acceleration detector. When you accelerate a lot, you feel it in your stomach, you know, like when an elevator starts to move, that feeling in your stomach is you detecting the acceleration of the elevator. So if you start out with a fairly big circle going 10 miles per hour, you feel a little bit of acceleration as you go around a circle, but not much. Okay, so now stay in the same exact circle. Don't change the size of your circle, but increase the speed to 25 miles an hour. Okay, do you feel more acceleration or less? More, and that's why this, I mean, you wouldn't right away jump to the fact that this speed would be squared, but it makes sense that the speed is in the numerator. So as the speed goes up, if the radius of the circle stays the same, the acceleration goes up. Okay, and now think about how the radius affects it. So now go back to 10 miles an hour around your original circle. And now try to stay at 10 miles per hour while you turn into a much smaller circle. Do you feel more or less acceleration? More acceleration as r goes down. Okay, so that r needs to be in the denominator. And so it makes sense that those are there. Then what about the fact that v is squared? Well, one thing that gives you a clue about that is it makes the units work out. So what are the units of, in SI units, what are the units of speed? Meters per second. So what are the units of speed squared? Meters squared per second squared. What are the units of radius? Meters. And so you cancel out one of the meters on top, and you end up with meters per second squared, which are the units for acceleration. So it all makes pretty good sense, but it's cool how simple it is to be able to just calculate the magnitude of that turning. You know, that's the acceleration that makes you turn in a circle. And no matter what you're doing in the circle, how fast you're going, whether you're speeding up or slowing down, the acceleration that makes you maintain that circular motion is just the speed squared over r. It's really simple. Any questions? Okay, so, well, that's it. That's all the new stuff. The total acceleration is, you know, just like for general motion, it's equal to the parallel acceleration plus the perpendicular. In circular motion, it's equal to the tangential plus the centripetal. And so once you calculate, you know about the acceleration, you can draw free body diagrams, go to Newton's second law. A lot of times you can use that to calculate forces. Okay, so I'm going to give you a general set of steps that work for all except one specific type of circular motion. I mean, it would still work for that, but there's a faster way to do it. So this is the general set of steps for any circular motion problem. Besides tetherball type problems. Tetherball type problems are ones where an object is just hanging by a cable and spinning around in a circle that's parallel to the ground. Okay, like the game tetherball, you know. What? Why would you play that? Oh, um, the reason is it just has to do with sort of a complicated system of like the angle of the cable is sort of in a complicated orientation with the way that you with the orientation of the circle itself. So it'll make more sense once we get to that later, and I'll just give you a specific way of doing those kind of problems. Okay, so the example I'm going to choose is imagine, so I'm going to choose this because I know how to draw trains really well. So good. Okay, so imagine there's like this toy train and it's in circular motion around a train track. That's the example I'm going to use for this. Okay, so the first step is you have to choose the view that you're going to take of this problem. So choose a view where the path is visible as a circle. Okay, so for the example here, the view that I drew there isn't the best view to take for doing the calculations. Instead of taking a sideways view like this, we want to take a bird's eye view, a top-down view, because then you can see, then what you're looking at is a circle, and that'll make the calculations easier. The way that the view matters isn't really just your way of thinking about the problem. It's how the coordinate system sits as you do the problem. So you need your coordinate system lined up in a way where the axes represent important quantities. So in this example, I would take a top-down view. You know, from underneath looking up would work fine too. And so then the coordinate system, I'll choose the origin at the center and the axes like that. And then the second step is you need to choose a point on the circular path that you want to analyze. In a lot of problems, it tells you what point on the circle you have to do. In some problems, it doesn't, so you just have to choose one. So I'll draw this again. Here's the coordinate system. And you can choose any point you want. For this one, I'll choose this. But I'll do a few different places so you can see how it works, as we go on with more examples. The one thing, always choose one of these 4 points here, here, here. Because if you don't choose those, you'll have to use complicated sine and cosine stuff to figure everything out, and it's just, there's no benefit to it. So choose one of those simple points. Step 3, draw a vector from the chosen point toward the center. That's the centripetal acceleration. And it has a magnitude of v squared over r. Okay, so we're looking at this point here. So the centripetal acceleration is this way. So what direction is that in? Positive x, positive y, negative y. Negative x, yep. So the centripetal acceleration is in the negative x direction with a magnitude of v squared over r, and then 0 for y. Step 4, if the speed is changing, draw the velocity vector and the tangential acceleration vector. Based on whether it's speeding up or slowing down. Whether the speed's increasing or decreasing. And this works just the same way it does in lab with the parallel part of the acceleration. If the speed's increasing, the tangential acceleration is in the same direction as the velocity. If the speed's decreasing, it's in the opposite direction of the velocity. By the way, if the speed is constant, the motion is called uniform circular motion. And if the speed is changing, it's called non-uniform circular motion. Okay, so we're looking at this point. There's the centripetal acceleration. The way I drew the motion before, the velocity would be this way. Let's say in this case that the speed is decreasing, then the tangential acceleration is this way. So here's the centripetal, here's the tangential. And is the tangential acceleration in this drawing in the positive x, positive y, or negative y? Negative y, and so then if you knew that it was changing speed at a rate of 8 meters per second squared, then that vector would be 0, -8. This seems like a lot of steps, but these steps are really short. Step 5, the total acceleration is just what you get from adding up the two parts. So the acceleration is a tangential plus a centripetal. And now once you have the total acceleration, you can draw a free body diagram and do Newton's second law. So I'll say step 6 is a free body diagram, and step 7 is Newton's second law. So I'll just do a few examples now. There's one new thing that you haven't seen before, but it's going to happen in some problems now. So notice, one thing that hasn't happened up until now is that some forces will, this won't always happen, but they'll sometimes be forces that act out of the plane of the coordinate system. So for example, in that train example, that's supposed to be the top of the train. I'm not so good at drawing those. So we chose to do this problem from like a bird's eye view. And so now when you choose what forces are acting on something for a free body diagram, the first thing you do is always the weight. But, our coordinate system is like this. So what way does the weight act in this? Well, just like point in the direction of the weight, or yeah, it is down, and in this picture it's into the page, you know what I mean? And so yeah, like how do you represent a vector into the page in a coordinate system that's a plane? It doesn't make any sense. You'd have to do it, well, we're looking at the top of the train, so its weight is like into the page the way we're looking at it. And so you'd have to do it with the z-axis, which we're not going to deal with. What? Oh, like the figure, the way you draw it, you mean? Yeah. It would be, well, okay, so I'll talk about that, but and then there's a second force acting on it that doesn't that doesn't appear in the plane of the coordinate system. In this case, the normal force would be acting out of the page, you know. So the weight and the normal force are out of the plane of the coordinate system. Okay, so there are two options. You can just leave off the forces that are not in the plane of the coordinate system. So like the weight, you can just draw your free body diagram with no weight on it if it's out of the plane. Or if you want, you can represent vectors coming out of the page like this. That's supposed to be the tip of the arrow coming towards you. And vectors going into the page like this. But whether you leave those vectors off completely or you draw symbols like this, it won't show up in the calculations. Okay, they're just not going to show up in the calculations. That's sort of a weird new thing that's going to happen sometimes. Any questions about that? Yep, we will. So any problem where the circle is horizontal, the thing's moving in a horizontal circle, the weight is going to be perpendicular to the coordinate system, so that'll come up. And if the ground is flat, also, then the normal force will also do that. So it'll come up pretty often. Just do what you, I think some people would like to label it just because they want to make sure that they've covered everything. And some people feel like the less work, the better, and both of those are acceptable. Yes? What? They will not. Because there's no way to represent a vector that's like into the page using a coordinate system like that. So it just doesn't, that coordinate system doesn't see vectors in it that are perpendicular to it. Yep. Oh, okay. So you'd have like mg and n, and then any forces that are in the plane would be like that, like we're used to, you know. Apple. I thought you were asking a question. Apples. Okay, let's do an example problem. Okay, so let's say that a plane every time I try to draw a plane, it looks like some kind of sea creature. The sea creatures don't have cockpits. Checkmate. Yes. Okay, so this plane is going this way, and let's say that we're going to calculate some stuff about this point right here. And at that instant, it's going in a circular motion with a constant speed. The radius of the circle is 250 meters. So this is the point P where we're going to calculate stuff. And the plane has a constant speed of 120 meters per second. And we want to calculate three things. So first, at point P, what's the acceleration? I mean, everything's accelerating together, but we're going to do all these analyses with the pilot as the chosen body. So what's the acceleration of the pilot? Second, all these are going to be at the point P. What's the force on the pilot by the seat? And I'm going to break that force up into a pushing force from the back of the seat and a pushing force up from the bottom of the seat. And then the last one is at point P. What's the force on the seat by the pilot? A and C are very reasonable engineering questions to ask, like if you know like a particular like a especially sketchy maneuver that the plane is going to have to do, you want to know if it's going to require an acceleration that could be dangerous. With a high enough acceleration over a long enough time, and all fighter jets are capable of doing pulling accelerations like this, the pilot can pass out. And if a pilot passes out, that's bad for the pilot and the plane. So you want to avoid that. So that's a totally like a calculation that people would do all the time. And then you can't really think of a super practical reason why you would want to calculate the force the seat applies to the pilot, except you would, as you're putting components into the plane, you're choosing how to build the seat for the plane up. You would want to know what kind of force the pilot is going to apply to the seat so that you know how thick the steel in the seat needs to be and stuff like that. And so the way we're going to figure out the force the pilot applies to the seat is we're going to calculate the force on the pilot by the seat and then just use Newton's third law. Okay? Any questions about this? Okay, so let's just go through the set of steps. The first time on this first example problem, I'm going to break it all up, like write out the separate steps one by one. In the next example, I'll do it all sort of on one figure because obviously sort of doesn't make sense to keep drawing the circle with a new thing on it each time, Okay, so step one, we have to choose a view. And we want to choose a view where the circular path is visible. In this problem, that's the one that's drawn, so we'll just use this. I'm not going to do it like that. That's ridiculous. I'm not going to draw this circle over and over again like a sucker. Okay, so it's going this way. Here's the view we're going to take. So the coordinate system is like this. in this problem, we're told what point we need to investigate. So I'm going to put that right here. Now draw a vector from that chosen point toward the center of the circle. So there's the centripetal acceleration. And that's in the negative x direction in this case. And also, we happen to know the speed and the radius of the circle already, so we can calculate what that is. So the centripetal acceleration is in the negative x direction with a magnitude v squared over r. And v is 120, and r is 250. And so this comes out to be negative 57.60. That's in meters per second squared. In this problem, is the speed changing? No, it says it's constant speed. So is it uniform or non-uniform circular motion? Uniform. Okay, so the total acceleration is equal to the tangential plus the centripetal. This one's 0. And so the total acceleration is negative 57.60. They were constant speed of 120 meters per second, and the radius is 250. Now we can do a free body diagram, and now we're finally ready to go to Newton's second law. If the point we're looking at is this point P, the plane would be going straight up at that instant. So the pilot would be sort of like looking straight up into the air, like he's lying on his back. So a free body diagram of the pilot would look something like this. The weight force is acting this way. Oh, I didn't give a mass. Let's say the pilot has a mass of 100 kilograms. Okay, so the weight is 100 times 9.81, so 981. And now we have to go around the boundary looking for contact with the surroundings. I said I'm going to consider that contact to occur in two spots. There's going to be a force from the seat part of the chair pushing this way. I'll call that F chair. And then there's going to be a pushing contact on the back that I'm going to call F back. And we're ignoring the any force with the steering wheel or whatever. So this is it. Okay. Any questions about the free body diagram? Yeah, you could think of either one of these. You could think of as a normal force. A normal force is always just a pushing contact between a surface and a thing. So yeah, it would be, if you wanted to call those N1 and N2 or something, that'd be totally, a lot of people would do that. Okay, and now Newton's second law. Our coordinate system is this. So the weight force is 0, negative 981. the force on the back, that's in the positive y direction. So 0 F back. The chair force is in the negative x direction. So negative F chair 0. And all that is equal to 100 times acceleration, negative 57.60. And now we can calculate those two variables. The x equation says negative F chair is equal to negative 5,760. So F chair is 5760 newtons. And then the y equation says negative 981 plus F back is equal to 0. So F back is equal to positive 981. And so now if we want the force vector on the pilot by the chair, that's actually both of these two things added together. So this is the force vector on the pilot by the seat. So just substitute those two variable values we just found into those vectors. And you get that the force on the pilot by the seat is equal to negative 5760 positive 981. And then the last part is just Newton's third law. If we know that the force on the pilot by the seat is this vector, then the force on the seat by the pilot is just, switch both of the signs. And so it's 5760 negative 981. And so this is a number that you would use to evaluate how strong the seat needs to be. Anyone have a feel for how big this acceleration is? Could someone stay conscious with an acceleration like that? I think if it went too long, it would be a problem, but quickly, I think it's not really a problem. But when people talk about an acceleration, if you ever see like a thing, people talk about fighter pilots, they talk about how many G's they're dealing with, and talking about is 1 G of acceleration is 9.81, and so this is a little less than 6 G's, and so that acceleration at that instant is about 6 G's, and for a very short time, a normal person could stay conscious, but after more than a couple seconds, I think a normal person would pass out. Pilots train like tricks and stuff to keep from passing out, and they know how to handle like a little bit bigger accelerations, but I don't think anybody could deal with that for too long. This is supposed to be the clouds are up here and the ground is down where the questions are. Yeah, right. Yeah. But whatever plane you choose to do the circular motion part is going to have to be the plane you choose. You're going to have to stick with it for the free body diagram and stuff. So if you choose a view where you see the circle like that's going to have to be the same view that you use for your free body diagram. Otherwise, your vectors will all be off. Mhm. For what? You're right. You're to the side of it, looking at it from the side in this case. That's right. Exactly. And that's why in this case you can see the weight force. If you're doing one where you're looking down at it or up at it, then the weight force disappears from the problem. Any other questions? Uh, okay, let's stop there. And I'll do a couple more examples next time.